mistake as everybody thinks.
Not your last mistake.
It's yeah, it's right. And I want to start with some words Remco said on Monday. So have in mind we are mathematicians, so we're doing math here, but on models which are somehow inspired by the real world. And in this conference, this means, of course, graphs. Maybe also I learned that it should be hypergraphs, but I don't know how to do that, so I stick with graphs. And so we want to have models which have the properties we learned about already. Like we want to have models that are scale-free in the sense we have a power law degree distribution, so we have a high variety in the degree distribution, so we have like normal vertices with an average degree, but also some very influential vertices with an arch degree. We want to have clustering in the sense that similar vertices are somehow more likely being connected than randomly chosen vertices, but maybe we don't want to be too strict here because still on sometimes not very similar vertices which are not powerful as well should still have a chance to connect. And on top, we want our graph to be sparse. That means the number of edges should be of the same order than the number of points. And once we have a model with those, let's say, basic properties, we want to see what can we infer from here. So if we combine those effects, what follows? And so let us start with the model. We are taking a spatial random graph here. So our vertices are embedded into spaces. Here on this picture, space is the unit interval you see on the bottom. And the idea of embedding the graph into space is the following, that the geometric position models on an abstract level like intrinsic properties of the vertices, so that two spatially close vertices are considered to be similar. Then we attach a mark to each vertex. The mark is distributed independent from uniform distribution on 0, 1. And maybe from the first hand, a little bit counterintuitive, small mark now should measure a high influence on the model. So you can see the uniform mark as the inverse of the weight, if you prefer to think in weights. And then combining both effects, we connect. So we see here at the, I should use this. We see here maybe an influential vertex because it has a small mark, so a high weight. Then vertices are connected because they are close to each other. And one comment on this curly edge here, we want to avoid boundary effects later, so we work as a torus, so we glue the boundary together, so to say. So actually those vertices here with the long curly edge, actually they're close because they're close to the boundary. So this is the idea how we want to build our model. And let's do this more precise now. So for the graph Gn beta, we specify beta later. We sample a number of Poisson vertices, precisely Poisson n. You could also do n vertices right away, but I prefer a little bit more randomness. And we embed it into the unit cube. Then we add our uniform distributed marks. Yep, now there was a mistake.
There you go.
I mean, you wanted to see it anyway, so. And just for further reference, so our vertices now have two components, namely a location x and a mark ux, and together we write it as a bold x. And for the expert here, the collection of the vertices you can also think of as a homogeneous Poisson point process on the space of the unit cube type the 0, 1. Actually, this is one of the reasons I prefer doing marks than weights from the beginning, because your Poisson process keeps homogeneous. And, Remco does it otherwise, so maybe we can discuss it later. Right, and if we have two vertices, or we have sampled all our vertices, we connect each pair of vertices independent with a function which has all our ingredients, namely beta, which is parameter of the graph, the marks, and the distance, and let's have a closer look. So it is a decreasing function. We have here a polynomial decay outside. Maybe one comment for the computer scientists here, and for me means minimum, or for me means maximum. And if you play this game with 0 and 1, then it's consistent. So we have a cutoff here at 1. Okay, we want to have a probability, so this makes sense. And then we put all our input here. So it is a decreasing function. So we have this 1 over beta in here. So if we make beta larger, all the input in there gets smaller, so the probability increases. So beta is our edge intensity because it increases on average the number of edges if we take the same sample, but a larger value of beta. Then we have the vertex marks here as a, now I maybe want to get rid of the mouse, which enter as this product structure. So we take the smaller mark, give it the exponent, and multiply it by the larger mark with a different exponent. And somehow that's the way how we want to measure the influence on the marks on the connection probability. And here we see if we make our marks smaller, then this factor gets smaller, so the whole input gets smaller again, and the probability of connecting increases. And we'll see more like some examples, what are good values of choosing gamma and alpha, our exponents later, to make it more like, realistic, no, maybe not realistic, but to have some feeling what those exponents are good for and why we've chosen that. We have some restrictions on gamma and alpha. We need them to later have sparse graphs. So if we make the influence of the vertices, of the vertex marks too large, we lose finite degrees or finite expected degrees, and that's not what we want to do. And then we have the distance here. I wrote it as a d because we have this torus metric, what I mentioned earlier on the slide. So it's essentially the Euclidean metric, but we glue the boundaries together. So, right, and what we have to do, we have to scale the distance by the expected distance of its nearest neighbor, because we have a finite or volume 1 cube, and we add more and more vertices if we take large n. And of course, we want to have in each step, doesn't matter which n we take, the connection probability should look the same. So we need to rescale the distances. I scale also the dimension by the dimension d here, with just its modeling approach to choose my other parameters independent of the dimension. And the last parameter is this exponent over here, which is called long range parameter. Why is it called like that? So imagine this, let's call it mark scaled distance is small, in particular smaller than 1. Then we have something smaller than 1 to a negative power, which is too large for being a probability. So we cut it off. We are in this case, and we just connect the two vertices. So this is when always a situation when they are very similar to each other. So the distance is short, or one or even both vertices are very powerful and have very small marks. And if it's not the case, still I have a positive probability of connecting the two of them. And how large this probability is basically determined by this parameter delta. And if you do it, indeed, you can very easily compute that you get two of the features you want to have. You get your power law degree distribution. I prefer power law degree distribution over the word scale free, because we have a spatial setting here, and then scale free, which does not refer to the space, is also a little bit confusing. So we indeed have a power law distribution, 1 plus 1 over gamma. I write it down here just for us. It's easier to remember. If you are online and can't see the board, I'm sorry, you have to remember by yourself. And we see here, because gamma is in between 0 and 1, because Remco told about the importance of the case tau being in between 2 and 3, it's precisely when gamma is in between 1/2 and 1. And also because of the dependence of the distance, we observe clustering. Right, here's the overall page again, what we do. And now for proving later, for modeling, I think that makes sense that the vertices enter the network and the space is somehow fixed. What you can also do for proving, you change it slightly. That doesn't change the law of the graph, but just a little bit the setting, how it looks. Basically, now you take the cube of volume n and don't rescale the distance anymore in the connection probability. Then by law, it's the same thing. You basically just moved the scaling from one position to the other. So in law, it's the same thing. For proving stuff, this is actually sometimes a little bit easier. Okay, let's do examples. We have two important examples for the talk. The one is the long-range percolation model, which is essentially the model where there are no marks. So gamma and alpha, our exponents for the marks is just 0, which takes them to totally out of place, which then leads to, let's maybe here, long-range percolation, leads to the connection probability 1 minimum over this thing. So if you can see here, if the distance is small, you connect the vertices depending on your value of beta. But if the distance is large, you have to trust your luck. And the second one is currently one of my favorite models, is the soft Boolean model. And I like it because it interpolates between this model, long-range percolation, which is kind of well established, and another well-established model, the so-called Boolean model. And it works as follows. So the marks now play the role of radii. So you take your gamma. That was the same mistake again. You take your gamma here and take your marks and create radii distributions, which are Pareto with exponent determined by gamma. Pareto here essentially for me means just, okay, here's another Pareto, but it has a polynomial tail and everything is larger than 1. And you connect in the classical Boolean model, you connect two vertices that's down here whenever the larger ball contains the weaker vertex. That's a well-established model. Now, additionally, for the soft Boolean model, for each potential edge, you draw another independent heavy-tailed edge weight, and then you scale or enlarge every radius by it. But it's a different edge weight for each potential edge. So like you have like varying radii for each possible connection. And so we see here in the center, even though the large vertex, it has a large radius, but they had bad luck with the weight, so they still can't manage the connection. But the two not so strong vertices, they had a lot of luck with their edge weight, so they can now make a connection. And this model basically interpolates very nicely between long-range percolation and the Boolean model, because if we send delta to infinity, then essentially the edge weights are all 1, and we are left with the classical Boolean models. And if we send gamma to 0, basically all radii are 1, and we are left with just the long-range percolation model. But you can do other stuff. For example, you can use scale-free percolation. There you add weights to the vertices and multiply them. One of the et al. Authors I mentioned is in the audience. It's Remco. Also with like Gerard Houriemstra, if I pronounce this correctly. Houriemstra. We already saw his names on the slide on Remco's talk. The edge-dependent random connection model, also a model, of course, I can recommend. It's from my former group in Cologne, which is a preferential attachment approximation, so to say. And also a little bit older model, maybe the ultra-small random geometric model by Lukas. I just added it here because it's also in the framework, and it is different in that sense from all the vertices here, because in the first 4 models, the heavier vertices are important for the connection, and in Lukas' model is actually the weaker one. But let's not focus on that. I just want to mention that actually it's quite a general framework, and you can fit a lot in there. All right, So I'm interested now in the existence of a giant component. So what is a giant component? We say the graph contains a giant component if its largest connected component is asymptotically of linear size. And I also want to focus now on dimension 1. Why do I want to focus on dimension 1? Because in dimension 1, the geometric restrictions from our embedding are just the hardest, because I have no space to like evade like weird regions whatsoever. The higher the dimension, the more regular the space gets. And in dimension 1, it's the hardest. Typically, also a part of the definition of giant component is uniqueness, that we can kind of get here for free because our model is ergodic. So basically, we want to just check whether there is a giant component or not.
So you know that the giant component will be used?
Yeah, it's the classic. I tell you the names. Burton-Keane argument. Trifurcation points. Yeah. Yeah, right. So yeah, I can. If time in the end, I can tell you how this trifurcation point argument works, but maybe not now. So, and we want to identify an easy parameter which depends on our building properties that tells us essentially whether there is a giant component or not. And this thing will turn out what we call effective decay exponent, delta effective. Well, delta because the decay exponent of the connection probability is delta, and now it's the effective delta. And it's defined like that. So what do we have here? Let's just focus on the integral. So we have in the integral, we have the connection probability of two vertices at distance n, and integrated from 1 over n to 1. So if you imagine you have n vertices here, then you have a gap of n, and then you have another n vertices here. In each of the sets of size n, the minimum mark is of, so the minimum mark, which means the highest weight, so to say, is of order 1 over n, or that's what you expect to see. So this integral is basically nothing else than just from the two sets of size n, you choose a vertex uniformly at random here and a uniformly at random here, and then ask, are they connected or what not? And with the log, and lim structure, basically, in the end, you are left with the exponent, how this expected probability, so to say, decays. So it's like very connected to the actual delta, but it also takes into account how the marks influence now these connections over a long distance. And here you can have our main theorem that indeed knowing delta effective is enough in dimension 1, because you can distinguish when delta effective is smaller than 2 and you choose a large enough beta, then you will have a giant component. But if delta effective is larger than 2, you will never have a giant component. So there's a phase transition, or a possible phase transition in beta when delta effective is smaller than 2. And I hope I can give you some intuition why this is the case later on, but first apply this to our main examples. So in long-range percolation, there are no marks. So if you check this integral here, basically there is no integral, it's just n to the minus delta. So delta effective equals delta in that case, and which is actually known that if delta effective is smaller than 2, or delta smaller than 2, then you have a critical edge intensity upon which you have a giant component. But if delta is larger than 2, you can never have this. In Boolean model, where the radius distribution is determined by that gamma and between 0 and 1, it's known you will never have a giant component in dimension 1. So, and what happens if we combine those? For my favorite model, here actually we see something interesting, because we see a transition which depends on both the dimension, not the dimension, the geometric restriction modeled by delta and the gamma modeling the radii. Of course, if delta is smaller than 2, already the long-range effect is enough for giving us a giant component. But if delta is larger than 2, so we have quite some hard geometric restrictions, still I have a phase here which does not only depend on gamma, but also on delta, where there is still a giant component. And if we remember the power law exponent, it's a sub part of the tau equals 2 to 3 phase, but it's not the power law exponent alone which determines this phase here, which is quite interesting in my opinion. All right, how do you prove it? All right, here have samples. So above there is a delta effective smaller than, I forgot the precise values I took, but above there is an example with delta effective smaller than 2, and it's basically a connected graph. And below you see, of course, it's not a lot of vertices, so potentially in the limit something else could happen, but you already can see like all the finite components here. And I think below I took gamma slightly smaller than a half, so still we have no variance in this picture, but like all those finite components already. So we can really see our results here. Okay, how do you prove it? We rely again on something which was mentioned before, namely the weak local limit. We want to basically know how our graph looks when the number of vertices tends to infinity. And indifferent to many non-spatial models, a weak local limit for us is fairly easy to construct, because we take a Poisson process on the real line, we add a root vertex, call it 0, so we place it precisely at the origin, give it a uniform mark, so we get a so-called palm version of the Poisson process, which you can think of as the following. You have a vertex with a uniform mark precisely at the origin, and from there you have like to the left and to the right independent exponential random variables, which always gives you a distance to the next point. And you can go basically on forever and construct your Poisson process. And then we build our graph precisely as we did earlier. Just now the torus matrix replaced by the Euclidean one because there is no more boundary. And indeed,
Sorry,
yeah.
the origin doesn't matter because you're on the torus.
Yeah, well, now I'm here on the real line, so I want to have it on the, but the torus will be important later, just in a second. So I basically here I built an infinite graph on infinite many vertices on the real line, where I know one vertex which is at the origin. Yeah, right. And basically that's the reason why it was important before to work on the torus, so that we have a shift invariant space, because if we now take this infinite graph I just constructed and restrict it to the interval of length n, then in law it's just the same as a graph Gn which we constructed earlier, but with a typical shifted such as a typical vertex, which is a uniform chosen vertex, is at the origin. So basically, because we somehow need to, we use this, it's called palm distribution, and actually this makes it much easier than in many let's say non-spatial models, where you much smarter how you actually choose your uniform vertex when you go to the limit, right? And then you can actually see that we actually have our limit structure here. So whenever I have an event that depends on the root vertex and a bounded graph neighborhood, in the limit both probabilities coincide. Here in this setting, you can actually do this proof by hand for much more general models. Remco has a paper with his PhD student. So this is well established. And basically, if you have this limit structure, you immediately know stuff like degree distribution or clustering, because now you know how you calculate it. But for the giant component, this is not enough, because giant component relies on the entire graph and not only a bounded neighborhood of a vertex. Yeah, right, but you have to show that your survival probability is not 0, right?
An analysis of the limit.
Yeah, right.
But you do have conversions of the giant into deterministic constant, which is stronger than what you were assuming of your base method. You were saying that it contains epsilon endpoints. Now you know that the giant divided by n will always converge to the constant will be 0.
Yeah, right.
But if in your setting it's ordered to the natural, then you actually know also that the constant is positive.
Right. So what Remco just said is what I wanted to say. That you don't, because of work he's done, you don't need much more than your limit, basically, because in a general setting, you need a little bit more. For us, it's basically enough to study the limit and to say, like, is there an infinite component in the limit or not? So that's what we have to do now. So yeah, maybe, I don't know when I started, so I just keep talking until you stop. 5 minutes, perfect. So let's just maybe go with the intuition, because and just make the proof for the long-range percolation, where there are actually no correlations and all edges are independent, because this is paradigmic basically for our proof, but our proof then just contains a lot of nasty decorrelation and stuff, which you can read in the paper if you're interested, or ask me over coffee. Then I refer you to the paper, and so, but the long-range percolation is paradigmic. So let's start with the case that there's no infinite component. Basically, what you do, you calculate the number of edges that cross a certain point. So you fix a point, maybe slightly below, left to 0, because on 0 there is a point, but slightly left to 0. And then you ask how many edges crossing that point. So you integrate in that direction, you integrate in that direction, and the integral tails is of the order n to the minus delta. You do this twice, so you end up with n to the 2 minus delta. And then either this goes to 0, as either this is integrable, then you know with a positive probability there is actually no edge. And then you know by ergodicity that you find gaps which are not crossed by an edge infinite often in the graph, and whenever you find those things, your component ends. More interesting is the case when you actually have a delta smaller than 2, because there you need to be a little bit smarter how you use this idea of comparing connecting two sets of n vertices at distance n. And I think it's quite fitting because it's based on a renormalization scheme by Dominique Coupon, Gavon, Tassier. So this is Fields Medal winning material here in Fields Institute. And what you do, you divide your, you take your Poisson process. Of course, I draw it here more like a lattice, but it's, well, you take your points and then you form boxes of a certain number of points. And for super exponential, like very large, no, very fast growing scales. And you do it in a way that two consecutive boxes overlap on half of their points. You see, like the red and the blue box, they share half of their points, and the blue and the green as well. And then you say a block is theta good if it contains a connected component of density at least theta. That means we change, so we now want to say, like, okay, a component is good if it has a kind of dense cluster. And now we choose a theta which is at least 3/4, because then we know by the overlapping property that if two consecutive blocks are good, their largest cluster needs to intersect in at least one point. So basically, you know, if on the scale Kn, like I look at the large scale, this is divided in scale n-1 boxes. And if I, for example, knew that all of those blocks on the scale n-1 are good, I knew all their clusters would intersect. So the box one scale up is good. And if it's not the case, basically I know there somewhere in the middle there's a bad block, and then I have my strategy of jumping over this bad block with a long edge and still end up with a good enough cluster. So to say, that is the idea. And then my beta in the end, I only need for the very first scale to say, like, I start with a decently dense cluster. So that's why it doesn't work for every beta, but only for a sufficiently large one. Right. This is basically what I wanted to say. So just two comments. So you can use delta effective also in other contexts, not only dimension 1. So for example, Benedikt, Jane in Berlin and I managed to say, like, whenever delta effective is larger than 2, there must be a subcritical percolation phase. Christian Mönch managed to show that if delta effective is smaller than 2, then the infinite cluster of a graph is transient. And I also want to give the more computer scientists here, or statisticians, something to think of. So far, delta effective here for me is a pure theoretical thing of my graph, right? It's nice because it's fairly easy to calculate and gives me some results. But what does it actually mean? Because it somehow measures the amount of long edges in the graph, where long edges is maybe something like the connections between not too similar vertices. And the first question is, does my network has geometry? And which one? So which dimension I should embed it in? Maybe Pavel can tell you more about that. And say I know the geometry, so I have my embedding. It's still not super easy because delta effective is defined over scales, because I basically zoom out and then count longer and longer edges. How do I do it properly, this scaling out? In the long-range percolation case, when there are no correlation between edges, it's not too difficult because then I can just use the empirical edge length distribution, but I don't know how you would do it, like applied in a good way for like real networks. Yeah, this is basically what I wanted to say. I want to stop with a picture. It's not a great picture I took when I visited the National Aircraft and Space Museum in Washington this weekend, because they asked, like, how do fast long distance connections affect your life? I think a lot of this workshop is about that. And at least if you live in a one-dimensional world, you want to have enough long edges to live your cosmopolitan life, because otherwise you are stuck on your one-dimensional island forever. And yeah, thank you.